So I'm about to illustrate the oxygen hemoglobin dissociation or association curve in detail. Currently, I am in a student meeting, but you cannot see the students' names or hear their voices. I can hear their voices, so that means they can ask me questions as they pop up. If I'm asked a question, I will rephrase what the question was, and then I will be able to answer that specific question, which means those of you watching the videos have the benefit of some feedback that I might not anticipate. So I think that's a good plan. Okay, so I'll go ahead and start my illustration just with the X and Y axis on this curve, because even just understanding what is on the X and Y axis is a bit of a struggle for students. So the X axis is actually partial pressure of oxygen, which means like concentration of oxygen. So it's like environmental oxygen, oxygen that is around, right? So you inhaled a certain amount, a certain volume, a certain quantity of oxygen molecules. That gives it a sort of concentration, that gives it a partial pressure, that creates a gradient. So that's just like environmental or inhaled oxygen. So as you know, oxygen likes to hang out as an O2 molecule. So it's two that are very strongly bound together. Okay, now on the y-axis, what you actually have is hemoglobin saturation. And this I actually like to express as a percent. Hemoglobin saturation, which can be expressed as a percent if you would like. So it's the percent of oxygen, or actually the percent of hemoglobin that has O2 bound to it. Now, think of it this way. You've got your 4 subunit hemoglobin. You can have no oxygen molecules bound to it. You can have 1 oxygen molecule bound to it. You can have 2 oxygen molecules bound to it. You can have 3 oxygen molecules bound to it. And potentially you can have 4 oxygen molecules bound to it. So this would be expressed as 0% saturated, which means there's no oxygen bound to that hemoglobin molecule. This would be 25%. This would be 50%. This would be 75%. 1, 2, 3 out of 4, 75%. And this would be 100% is actually bound. So I like labeling these specific landmarks because it perfectly reflects our understanding of fractions, percentages, right? So far, so good, everybody? Oh, sorry, guys. All right, the students in the meeting were not able to see the screen, and I just fixed that and got everybody caught up. So the next part here, now that we understand the y-axis is expressed as a percentage of oxygen actually bound to hemoglobin, we can start to illustrate what a standard curve would look like. So of course on the x-axis this way means more environmental oxygen. We would express this in millimeters of mercury, Hg as opposed to Hb for hemoglobin. It's almost like Hg was already taken by mercury, so we just went with Hb for hemoglobin. Now I'm not numbering my x-axis, which is not great science. But it's also a rough illustration. It's more conceptual. So just be aware that I'm not labeling this x-axis, and so that might make it slightly different than what you would find in a textbook. We're just going for understanding level here. So we start with our standard curve with standard temperature, standard acid-base balance, everything's standard. When everything's standard, you have a pretty direct connection between environmental oxygen and how much oxygen is actually bound to hemoglobin. It starts as a pretty straightforward curve. You increase oxygen, therefore you increase oxygen saturation. That makes a lot of sense, right? Does that make sense to you guys in the meeting? Okay. Now, we do find that every time something binds to a protein, that protein does change shape. So initially you have like a good increase here. It gets easier for oxygen to bind. It's actually very difficult for us to reach 100% saturation. Now, your textbook specifically phrases that every time an oxygen binds, it gets easier. I don't think that's true when you're talking about this very last O2 molecule. I think it's more difficult for that very last O2 molecule to bind. We do see that a lot in chemistry. The more things you bind onto the end, the more complex the molecule, the more difficult that binding is. So you get this sort of slope here at the end where it's no longer, I have it going up to 100%, but actually I should probably lower that a little bit and say it's not quite going to make it to 100%. This oxygen hemoglobin dissociation curve, we never quite get to 100% saturation of hemoglobin with oxygen. It never quite gets there. So even if you pump this person full of 100% pure oxygen, they're never going to fully saturate 100% of their hemoglobin. That is a lot to do with, we have to get that oxygen to the tissues. It has a lot to do with binding properties. And that's just the standard thing. It's, again, I think I mentioned this in lecture, it's like diminishing returns. You put more into it, but you're not getting as much out of it. That's how this curve always ends, even in standard environmental temperature, acid-base balance, everything. Now, this is the normal, and let's say that, let's do like a dotted line here. When you're at 25% oxygen hemoglobin saturation, here is the quantity of environmental oxygen that you need to achieve that, and we'll use that as our reference point. Is that making sense? Is that reference point making sense as a starting place? Does everybody understand what this dotted line means? Okay, that was a yes. Now, several features, several different things can cause what we call a right shift in this curve, and several things can cause what we call a left shift. F in this curve. Now, it's a graph, so it's our right and our left. It's not anatomical right and left. So I always illustrate right in red because that's my habit, and it, for me, intuitively works with some of the things that cause right shifts. A right shift looks like this. And what it means is that if we want to get to 25% hemoglobin saturation, we're actually going to need more oxygen to get there. This is a looser bond between oxygen and hemoglobin. This is more likely to dissociate. So it dissociates sooner, more easily. It'd be cool if I could write an A. Okay. Dissociate, yes. So the question was, is this more likely to dissociate? Yes, this is more likely to dissociate. And that it could be because this is a disease state and it's problematic, or it can be that physiologically we need to release more oxygen into tissues more quickly. So it could go either way. I don't want you to pigeonhole this into, right and left shifts are always bad, or they're always a disease state, and I also don't want to shoehorn you into right and left shifts that are always physiological. It could be either one. Now, a left shift, likewise, is going to look like this. And what this means is that if we want to get to 25% saturation of oxygen on hemoglobin, you actually need less oxygen to get there. It's a tighter connection. The molecules are more closely associated. So oxygen associates. It's easily. Running out of room over here. So let's start to look at the factors that cause these shifts. Now, the simplest one for me is temperature. Temperature, in my opinion, is the easiest way to conceptualize a right and a left shift. So if temperature, and this is my annotation for temperature, it's a T with a little degree sign, as in like 36 degrees, 37 degrees, 38 degrees. It's just an annotation for temperature that I personally use. I don't know that I've seen it everywhere. So an increased temperature is one of the things that causes a right shift. It's one thing that is going to cause a right shift in the oxygen hemoglobin dissociation curve. So if you have a fever, if your body temperature is elevated, what you're going to see in that scenario is that oxygen is going to be released from hemoglobin more easily. That actually, during a fever, helps us oxygenate tissues. You may remember from our immunology lecture saying that one thing that fever is good for is speeding up metabolic processes. So if your fever is causing you to release more oxygen into tissues, that helps you do more cellular respiration, that helps you increase your ATP production, which helps you do all of those metabolic activities that you need to fight that fever. So it could be a good thing in that case, or, you could be standing next to a volcano and maybe in that case we have some problems arising because of this change in oxygen concentration actually being released. Or maybe it doesn't hold on to it long enough to get to tissues that it needs to get to. So again, it can be physiological or it can be problematic. So that one's pretty straightforward. Elevated temperature, when you put heat on molecules, molecules tend to move faster. It's a form of energy. So that dissociation, to me, if you've got any chemistry background, makes a lot of sense. Is that a comfortable connection for you guys? That heat and molecules connection? Good. Okay. Awesome. Okay, so likewise over on the left shift, very intuitive. It's just going to be the opposite. Decreased temperature. So again, low temperature, lack of energy in the area, that directly means that we are going to have less movement of molecules and they're going to be more tightly bound together. So, big fan of temperature. That one's really straightforward. Which brings us to acid-base balance, which is actually the thing in the meeting that prompted this recording. So let's talk about acids and bases, and then we'll get to the connection between acids and bases and carbon dioxide concentration. So remember, and this is just an aside, I'll just kind of do this down here, pH is on a scale from 0 to 14, and 7's right in the middle. If you go below 7, that's an acid, and if you go over 7, that's a base. So again, 7.1 is very mildly basic. 6.9 is very mildly acidic, so it's just anything. So acidic numbers, those are going to be low. Basic numbers, those are going to be high. Which does end up causing a problem with my little arrow configuration here. So you know that acids are based on free hydrogen ions, or just free ions technically, but we'll track hydrogen as the most common ion. Now, if you increase acidity, and keep in mind, increased acidity means a lower pH, which again, this arrow thing kind of trips people up sometimes. It's the problem with using annotation instead of being thorough. You can kind of choose one. If it's a more acidic environment, though, that does cause a right shift. That does move everything over to the right. It's an acid. It tends to disrupt connections between molecules, right? It tries to disrupt bonds. So when you increase acidity, you do decrease the pH, you do cause a right shift and cause dissociation between oxygen and hemoglobin. So far, so good? Good. Okay, likewise, if you decrease, actually, let's not use that arrow. Let's say you make it more alkaline, which is the same thing as more basic, which is the same thing as a higher pH. So you see on this side, the arrows all agree, but on this side, the arrows do not agree. So again, just be careful with your notation there. These all mean the same thing. That's all the same. That's going to cause a left shift. That means that an alkaline environment encourages a tight connection between oxygen and hemoglobin. So still pretty straightforward with that one. Yes, so CO2 changes the pH. So the question is, what does CO2 have to do with pH? And the answer is that when CO2 is in our blood, it travels in a variety of ways. We've now learned about carbonic anhydrase in red blood cells and how that's actually going to create carbonic acid. So let's go into black for this. Let's put it down here. So CO2 plus H2O. And then we get our carbonic anhydrase. And does anybody remember the molecule that is produced as a result of this? I'm going to pause it for a second. So the answer is we're going to get H2CO3. And that is carbonic acid. Now, this hydrogen right here, one of these hydrogens can dissociate, making this an acid, making this something, it's a mild acid, but it's still an acid. So if you have elevated carbon dioxide, if CO2 increases, you're going to get acid. And how does CO2 increase? How do you get an increase in carbon dioxide? Hypoventilation, yes. So it depends on your breathing, right? Yes, exactly. So the student correctly answered that it's related to breathing. We're going to be specific that it is related to hypoventilation. If you're not breathing enough, then you're not off-gassing the CO2. And if you're not off-gassing the CO2, then you're retaining the CO2. And if you're retaining the CO2 and it's in your blood, then you're going to have more CO2 plus H2O equals H2CO3, which is carbonic acid. Therefore, if you have elevated CO2, that's the same thing as increasing acidity. So if you have elevated CO2, you're going to have a right shift in your oxygen hemoglobin dissociation curve. So you see CO2, getting rid of CO2, taking an oxygen with respiration isn't just about getting that oxygen and getting rid of wastes. They actually affect each other. Having high CO2 is going to alter the way your body handles O2. And stop me if you have any questions. But as you might be able to intuit at this point, the simple opposite is going to be true on this side. And we're just going to have low CO2. It just means this won't happen, right? It's just the absence of this. No CO2, no carbonic anhydrase action, no extra carbonic acid. That means we are going to become more alkaline in response to having low CO2, which breathing pattern leads to low CO2? Hyperventilation, exactly. So you off-gas more of CO2, and that's going to lead to something, potentially, it's going to lead to something called respiratory alkalosis. Okay, I think this is where I'm going to stop my video. I'll give students one more chance to ask questions specifically on this video, and then I will shut it down with great thanks to these students. So any last questions that you want on the video? That sounds like a no. Thank you all so much for participating.